So the last time we started talking a little bit about the wave equation. So as an example, as a simplest example of what it means to the Lorentz covariance. So covariance just means for me that the laws of physics should look the same no matter what frame you are in. For the case of Lorentz and covariance, there could be other group transformations that we will talk about later on. But likewise, there will be a similar definition. Right? So, for example, it is supposed to be covariant under some group transformation. That means that under all change of frames under that whatever group transformation that we're talking about, the laws of physics should look the same. Right? But in this case, there's a very specific meaning, geometric meaning, which is that all the laws of physics should look the same. In all inertial frames. So what it means is that if you have x mu and your I element looks like that, then as we discussed, if you relate one frame, the x frame to the x prime frame through a Lorentz transformation and a translation, then in the x prime frame, your line element, firstly your line element would look the same. That's part of what it means to be covariant. And in fact, it's because of this symmetry that in the first case that we discussed last time, the wave equation. Right, this is an example. The wave equation takes the same form. So let me write it out explicitly at least once. So this is the wave. Yeah, I can use 5. So X is a collective. X is a collective label for the coordinates in your reference frame. So this wave equation takes this form in the X frame. Right? So in the X frame, it looks, so maybe I should say the X frame. And in the X prime frame, if the laws of physics look the same, I don't have to do any calculations. But I should be able to write it down right away. I should be able to write it down right away. I don't have to do any hard calculations if I know physics is the same. But of course, to formalize this statement, we do need to check, right? So to make sure that this is true, so let me just say, so if this is what we mean by takes the same form. Right? But mathematically, how do we guarantee that it is true? We have to make sure that the operations that we write down, when we formulate our wave equation, in this case, is the derivative, the wave operator. We can show that this guy is in fact Lorentz. Is a Lorentz scalar. Okay. And in this case is why. This is why this guarantees the Lorentz covariance. In this case, phi is a scalar as well. So this is a scalar, and phi is also a scalar. I should say R, right? So R Lorentz scalars. So both of them are Lorentz scalars. So that's why this guarantees that the wave equation is Lorentz covariant. So I could say, in this case, I could say that it's Lorentz invariant as well, but I want to emphasize the word covariant because I specifically mean it takes the same form in all reference frames. And it does happen that in this case it's a scalar, so it's also invariant in the sense that it's actually the same thing. Right, so there's a number, right? At each point in space-time, if this quantity is evaluated at the same place as this quantity, well, it's zero. So both of them are zero everywhere in space-time. So it's a number, and that number is the same if you're talking about the same point in space-time. So in this case, it's a scalar. But later on, for example, we'll do electromagnetism, and it wouldn't be a scalar anymore. Yeah, so maybe I'll write it down just as a quick explanation of what it means. So later on we'll do electromagnetism, and we'll find that in the X frame, this is what the laws would look like. By the way, I will usually not write the derivative like that. So this partial alpha is usually what I will write as to denote dx mu. And if I have a prime, I often like to use the prime notation. I'll write d alpha prime, and this means dx prime alpha. Okay. So this is the X frame. These will turn out to be the electromagnetic fields. So I'll say more about this when we get there, but I just want to show you what I mean by this is the electromagnetic current, the flow of charge essentially. And so if this is in the X frame, in the X prime frame, again, if the laws of physics take the same form, I don't have to think, right? I just put primes on all my indices, and that is the law of physics in my X prime frame. But in this case, it's not a scalar. So which means that these guys, the components of this tensor, are not the same as the components of this tensor. It's related through a Lorentz transformation, right? And likewise, the electric current is not a scalar. There are four components if you are in 3+1 dimensional space-time. So there's a definite way you can relate these two, right? And it's through this definite, well-defined prescription relating, just as you relate the coordinates, you can relate the tensor through such a coordinate transformation. That's how you guarantee that your laws of physics are Lorentz covariant. In other words, if you know one thing, that your null host, then through the Lorentz transformation, you can actually work out the laws in physics in any other frame, right? In such a way that you will see it will guarantee the Lorentz covariance. But this is also one place where this is the wave equation is one place where I thought I will build on this and take the chance to actually tell you something slightly different, but will also lead up to the quantum aspect. So this is classical. But first, let me add one more thing, which is a mass term. So we've seen this before. And so instead of just having a wave equation, or maybe I should say one thing. So why is it called a wave equation? So let me, in case, has everyone seen the wave equation before? Which is basic physics 101. Who has not seen the wave equation before? Okay, everyone has seen. At least nobody is. Okay, so then I'll just do the Klein-Gordon equation. I wanted to do the two-dimensional case first. But if everyone knows the wave equation, then I'm not going to do it. So the Klein-Gordon equation is just the wave equation, but with a mass term. Right? So in my mostly minus convention, it's going to be a plus m squared. If you ever see a Klein-Gordon equation with a different sign of m squared, it's because they're using a different sign convention. So again, if this is with respect to x, then the Klein-Gordon equation looks like that. If you are in the x time frame, then all you have to do is just put x prime instead of x. And so, again, I think this part should be obvious by now. Because the wave equation is a scalar, adding a mass term doesn't affect it. So m, in this case, is the mass. It will turn out to be the mass of the scalar particle. So it's not supposed to be obvious right now, but I want to do the classical version of this first, and then so you guys can, in fact, match it up with what we're going to do later on. But what I'm going to do first is actually I'm going to add a source on the right-hand side, right? And so the source had better be a scalar as well, otherwise it will break the Lorentz covariance of the Klein-Gordon equation. So what I'm going to do right now, as an important aside, is to do a Fourier transform in space. So if I look at a particular mode, so phi, now I'm going to break it, phi of x, I'm going to now break it into phi of t, comma x. Okay, and this is something I might do every now and then. If I want to highlight the time part of the x mu, which is, sometimes this will be, I will denote it as x0, but if I want to emphasize the time, usually I'll put it as t. I'm going to now decompose this in Fourier space. So if I'm in a d-dimensional space-time, this would be d minus 1k, d minus 1, phi tilde of t. There's a Fourier dependency of k. And then this is I, k, dot, x. Okay? So why do I do this? Let's come over here. you plug that Fourier decomposition into this equation, and you remember that this plane wave is a linearly, is a set of basis, right? This is a set of basis functions in infinite space. What you should find, I won't do the whole thing, but for example, let's look at the derivative terms. Okay, so if you take the space derivative, so this means, remember this means dxi, and I runs from one over just the space component, and you take the derivative of phi. What happens is that you're taking the derivative of if you do an integral over k, this integral sign just means this guy over here, and it's just that I want to write it as a shorthand. So this is phi tilde k of t to the I k dot x. Okay. And so I can write k dot x in the following way, right? So remember that k dot x in vector notation is ki xi. But because I'm using the mostly minus convention, this is minus ki xi. Right? Remember, when I move the space index, it costs me a minus sign. So if I want to write it down as, I better use a j. It's a dummy index, but because I use an I here, I want to avoid using the same symbol. So this is I. You do a Fourier integral, phi of k. So this will be e to the minus I kj xj. And so you see that what the Fourier transform does is that it converts the derivative, instead of acting on the phi, it now acts on the plane wave. And we all know how to take a derivative of the exponential. Right? It's a derivative of minus I k, kj xj e to the minus I kj xj. Okay, and when I take the derivative, I'm taking the derivative of x. So this will become, remember this is the sum over j, but it's only going to give you a non-zero answer if I equals to j, or rather when j equals to I. So this, what will happen is that this will give you minus I ki. Okay, because again, when you sum over j, the only thing that will remain non-zero is when you do dxi, which is 1. And so it will give you back minus iki e to the I k vector dot x. So I'm going to return to my dot product notation. So in other words, going to Fourier space converts your derivative into an algebraic multiplication by minus ik. Okay? And so what you should be able to do, I think it's your homework problem, so I won't do the whole thing. You will be able to deduce that the wave equation plus a mass term would in fact give you the following object. This is phi double dot. This phi tilde double dot is this guy double dot, so maybe I'll write down k here. And you have k squared. K squared is k dot k. K dot k. And then phi tilde, and then plus m squared. And then you have k tilde, phi tilde k, and this will be equals to j tilde t. Okay. In in other words, I also do a Fourier transform of J. Maybe I should write it down here. So JTX is also given by J tilde K T e to the I to the X. So this should start to look a little more familiar in case you're not familiar with the Klein-Gordon equation. What you should remind yourself is probably your first semester in undergraduate physics, right? The simple harmonic oscillator. So what's a simple harmonic oscillator? It says that X double dot, I better use a different symbol, Q double dot plus omega squared. Q equals to some force, some external force, right? Usually there's a damping, there's a friction term, because otherwise you get infinite resonance. Yeah, there's a potential to get infinite resonance, which you won't get in the Fourier case. But you should remind yourself of that, because it's exactly the same form, right? Except you're doing a Fourier transform. But that's the whole point. What you realize is that in Fourier space, each K mode, each Fourier mode of your field, of your Klein-Gordon field, behaves classically like a simple harmonic oscillator with an external force that's provided by the source. Right? So at the level of the wave equation, at the level of the Klein-Gordon equation, you will say that this is a source of phi. Okay? Because without J, we don't produce phi. So it's J that produces phi. Just like in the electromagnetic case, we'll see later on, it's the electric current that produces photons and your magnetic fields and so on. But once you go to Fourier space, you see that it's actually the production mechanism is very much like a driven harmonic oscillator. Maybe I should say driven harmonic oscillator. Okay. And so let me just emphasize. So classical Klein-Gordon is in Fourier is a driven simple harmonic oscillator for each K mode. Okay? And it will turn out, in fact, that once you quantize this, it is still a simple harmonic oscillator, but it will behave quantum mechanically. And what we're going to discover is that we're going to end up promoting these to operators. And this is also why when you take a quantum mechanics course, you'll always see the quantization of the harmonic oscillator, because it's so important that it shows up even in quantum field theory. In fact, most, I shouldn't say all, most of the concrete predictions that we extract from quantum field theory are based on this framework, that we'll review fields as really a sum of harmonic oscillators. And even when we quantize them, they're still harmonic oscillators, except they're now operators, they are quantized. And in fact, what are particles? The quantum particles that you see produced from, for example, the Large Hadron Collider, what are they? Is when you smash particles together and you inject enough energy that you excite these quantum harmonic oscillators from the vacuum. That's essentially what's happening when you produce particles. Okay. But we'll do more of that. I just want to show you the beginning of both classical field theory and give you a flavor of the quantum aspects that's going to come. What I do want to mention also is that there's a difference between the mass equals to 0 and mass non-zero case. Okay, so if you take the static, the static limit, what you will find is that if you have a j that doesn't depend on time, and you try to solve that wave equation, you'll find that phi will go like 1 over r to the d minus 3, where d is the number of space-time dimensions. Okay, this little d is Pascal and Schroeder's notation. I should have put it here. So it's the same here. D is the number of space-time dimensions. Okay. And so this is a long-range force in the sense that it's just a power law. Right? In particular, in 4 dimensions, is 1 over r. Okay. So in 4 dimensions, 3 plus 1. So when d is 3 plus 1, you will find that both the static phi and both the radiation part will go like 1 over r. Both of them will do that. But let's just focus on the n equals to n greater than 0 limit. For the d equals to 4, you'll find that for n greater than 0, it's no longer a long-range force. You'll find that it will go by e to the minus m over r divided by r. So I don't want to write down the d-dimensional case. It's a Bessel function, so it's a little bit too much, I think. But it will still be the same thing. If you take the long-range limit of that Bessel function, you'll find that it's exponentially suppressed like that. But this is enough to show you that compare this to this, right? So let's just do the 4-dimensional case. You see that when r is small, then the exponential is roughly 1. Then they are roughly the same. But when r becomes large compared to what? Compared to m. So compare the inverse m, right? Then you'll find that this force will be damped out very rapidly. So this is 1 over r. Right, so this is phi, and this is r. So let's say this is 1 over m. Right, so in the m, remember when h bar is 1 and c is 1, m is mass is energy, and energy is 1 over length. Okay, so 1 over m is the only length scale in this problem, and so what will happen is that if this is 1 over r, then by the time you reach here, so here by the way, this is called the Yukawa potential. The Yukawa potential will look like 1 over r, but by the time we are here, it will be much more suppressed than the 1 over r term. Right? So, and by the time you come out here, both are small, but the exponentially suppressed one will be much smaller. So this is what I mentioned, I think, at the very beginning of the semester, which is that if you have a mass, if your particle has a mass, and it ends up mediating a force, right? So if you take the gradient of this, it will give you a force. The gradient. Right, so if you take the gradient, there we go. All right. Good, very good. Okay, so so I just want to briefly highlight something that I've mentioned before, but I want to write it down explicitly. Right? So remember that lambda here is defined by the property that it preserves the metric. It preserves the special relativity flat metric. And but I don't think it's written down explicit forms of what it looks like. In particular, I mentioned that there are continuous transformations that we can relate, that we can associate with it, namely rotations and boosts. Rotations we've talked quite a bit about, but boosts not much yet. And for the discrete case, that is spatial parity, which means you just take v and send to minus v, or x going to minus x, but only for the spatial components. And then there's time reversal. So the connection of all these operations fall under this definition, where all of them would preserve the metric. But I think so far we've only talked about rotations and parity to some extent. So for example, so let me make it a bit more explicit. So if you have, for example, rotations, then because we're doing space-time now instead of just space, then all that will happen is that rotations will leave the time component. So zero, remember that zero is the time component. So this is the 0, 0 component. These are zeros, these are zeros. And what we talked about rotations, you just fit it in this 3 by 3 block inside this 4 by 4 block. Okay? And if you talk about spatial parity, if you do parity, then this guy would just simply be 1, and then minus 1, minus 1, minus 1. Of course, you can also flip the individual. Components, but for the most part, when people talk about parity, they're just talking about flipping all the 3 axes. And this is the place where I mentioned before. This is an operation in 3 spatial dimensions. This is an operation that cannot be connected to a rotation. Right? This has angles in it. There are 3 rotation angles in 3 dimensions. And this guy is not connected to this, because this guy has determinant 1, whereas this guy has determinant, this guy has determinant, this 3-dimensional block has determinant 1, whereas this guy has determinant, that's minus 1, and this is 1. Okay. But what about boosts? So let me talk a bit more about boosts, because we haven't talked about that. So it turns out that boost was what made special relativity so shocking at first. Right? It tells us that time and space can be mixed, and in particular, you can show that the general form of boost looks like this. For example, let's say we boost in the 1, 2 plane, the time and the 1 plane, then what will happen is that you have a cosh C, sinh C, sinh C, cosh C, and then you will have 0, 0, 0, 0, 0, 0, 1, 1. So which means you leave the second and the third axis fixed, but now you're mixing up the time and the space, the time and the first spatial component. And I claim that you can check this matrix will satisfy this. So for example, if you lose, for example, in the time and say the third axis instead, then this guy will look like cosh C, and then you go to 1, 2, 3, sinh C, 0, 0, 0, 0, and then you leave the first guy untouched, the second axis untouched, but the third axis will be cosh. Now, for rotations, I've done this exercise before. I don't want to do it. I can also think about rotating 1 and 2, 2 and 3, and so on. But I won't do that. I want to do it for boost because I want to show you a different character of the boost. Okay? So one thing that you notice is that when you write down the rotation matrix, and you Taylor expanded the rotation matrix, you'll find that the generator was permission. So the question is, what happens here? Let's try that. Okay. So for example, we can do this over here. So this is when C is 0. So by the way, C runs over the rails. Okay, and so this is another. This is one of the stark differences between boosts and rotations. Boosts can have basically an infinite range in terms of the parameter. You can go to an infinite boost if you want. Whereas for rotations, you're always limited to a finite range of angles. And so, roughly speaking, this is what's responsible to make for making the Lorentz group have infinite volume. I'll put it in quotations. I don't want to be too precise about this. Physics books usually are not usually not too precise about this anyway. But the main point is that because this has infinite range, as opposed to the rotation group. So the rotation group alone has finite volume. And what you will discover very soon, let's do it, is that the generator of the boost is in fact not permission. Okay, so let's do it. So when C is 0, cosh goes to 1, and sinh goes to 0. So again, we recover the identity, and that's not surprising. If you don't boost, you're not doing anything, so you should get the identity matrix. But what happens when you make the first order expansion? So remember, I always like to put a minus I up here. Actually, let's do this. Let's put a C first, and then I'll put a minus I later. And now we can Taylor expand. Right? So cosh is very much like cosine. It's 1 plus order c squared. Whereas sinh is much like sine, it goes like c plus order c cubed. Okay. In fact, if you remember, this is e to the c minus e to the minus c over 2. Right? And so the zeroth order term cancels. The first order term is c minus minus c over 2 is c. And so this is actually c 0, 0, and then 1, 1. And so if I want to put in a minus I here, I would put in an I, and then put in an I here. 0 everywhere else. Okay. Let me write it properly. I. Okay. And so if you look back at your notes, if we do the same thing for rotations, let's say you rotate the 1-2 plane or the 1-3 plane or the 2-3 plane, and you Taylor expand the cosine, Taylor expand the theta, you'll find that the generator, if you factor out minus I theta, the matrix multiplying that will be Hermitian. But this guy, you can see, is not Hermitian. And it's not a coincidence. It's not a coincidence, so it's not Hermitian. In general, let me just tell you a fact, right? The fact is that infinite volume groups, the technical jargon is called a non-compact, but it basically means finite volume. So rotation groups are compact. Whereas this guy is non-compact, whereas Lorentz group is non-compact. And the mathematical fact is that when it's non-compact, they do not have finite dimensional unitary representations. Can you guys see? I don't know, ink is very faint. Okay, so this is a finite dimensional representation. It's 4-dimensional. 4x4 matrices act on a 4-dimensional vector space, right? And so because it's finite dimensional, and because the Lorentz group is non-compact because of the Boost part, therefore you should not expect that you get a unitary representation. So why is that related to what I just said? So remember that the, let me just save this thing and then we can take a break. Remember that for continuous groups that, at least a part of the group that is continuously connected to the identity, we should expect that our group element, in this case what we call the lambda matrix, should itself be written as e to some e to the sum over the generators, right? So this guy is the sum over the generators. In particular, usually we write it with e to the minus I times some stuff here. If it is unitary, then your x, so if lambda were unitary, then x would be Hermitian. But this theorem tells you that it's not possible. Because it's not possible to have a finite dimensional unitary representation. So later on when we do fermions, for example, we'll encounter the same issue. That the Dirac spinner or the Weil spinner will transform covariantly in an unusual way, something that you've probably never seen before. But all of them will not be unitary matrices because of this mathematical fact. But when you realize it on a quantum Hilbert space, like the way I was writing it for the scalar case, the momentum eigenstates, those are infinite dimensional because it depends on the momentum, and those will be unitary, right? But there's there's a connection between them that will only become clearer after you quantize the random fields. Okay, I think we better take a break. Let's come back in another 10 minutes. Okay. So, what must X satisfy? Okay, so I'm going to assume that I'm just going to look at the continuous part of this group, meaning for now I'm not going to care about time reversal or parity. Right? I'm not going to care about it. I just want to know, particularly for boosts and rotations, what's up with this X. So e to the X as e to the X mu alpha and e to the X mu beta contracted with mu needs to give me eta alpha beta. Okay? And so let's work this out. So what will happen is that you get 1 plus X plus higher orders in X alpha beta. So this will be Kronecker alpha beta. This is alpha, I'm sorry, mu alpha. This will be Kronecker mu beta plus X mu beta plus higher orders. Eta mu equals to eta alpha beta. So if you multiply this out, you find that the 0th order term is this guy and this guy contracted with that, so you get eta alpha beta. The first order term is this guy with that guy, so that means you're lowering your mu index and it becomes nu. Alpha is sorry, let me get it down first. Alpha is this, and then you have nu beta plus, and then this guy multiplied by this guy multiplied by this guy gives you connector mu alpha x mu beta. I must be very careful with the placement of the indices here. Nu beta, and then eta nu. So that means that I'm lowering my nu index and becomes a mu, sorry. And this is all, and then the higher orders is x equals to eta alpha beta. But it's basically a Taylor series, right? So all I need to do is compare the x term. And what I have this guy canceling out this guy. And what I see here is I get x beta alpha because this is nu beta, plus x alpha beta equals to 0. So I have to be very careful here. I started with one up, one down because the Lorentz transformation matrix is one up, one down index. But I have lowered one index because of this guy, and the x with both indices lowered, you can see, is an antisymmetric matrix. Why? Because x alpha beta with both downstairs is minus x beta alpha. Right? So remember, this is a row, that's the column. That's now the row, that's the column. So when I swap the row and the column, it gives you a minus sign. That means that x alpha beta is anti-symmetric. Okay. And this is very similar to the rotation group, if you remember. Except that in the rotation group, the metric was just a bunch of ones, right? It's just a bunch of ones. So there wasn't an issue with up or downstairs indices. Okay? But in this case, there is. And so you're going to be a bit careful that it is both downstairs or both upstairs indices that gives you the antisymmetric generator. So, but otherwise, once you realize that x is to be antisymmetric, then you can construct it exactly the way we have done it for the rotation group, which is the x itself must therefore be a sum over all the basis antisymmetric matrices. So let me write it this way. Omega over 2 mu nu j mu nu alpha beta. And these are the basis. I'll put an I minus I there. So this is the basis. Let me put it this way. Minus I j mu nu is the mu nu antisymmetric basis matrix. Okay. And so alpha beta is the alpha row, beta column of the mu nu matrix. Right? So mu nu is the label for which basis matrix you're referring to. Alpha, beta are the components of that matrix. And just like with the rotation group, we will find that mu nu is antisymmetric as well, and therefore omega mu nu is also antisymmetric. Okay, and so you'll find that you'll find the following actually. You'll find that one way to write it is one way to write this is that J mu nu alpha beta is in fact Kronecker nu alpha beta minus Kronecker nu beta alpha. And you can check that this is a representation that will give you antisymmetric in both alpha beta and mu. Okay, so this is antisymmetric in both mu and alpha beta. The next thing to remember is that the reason why the generators are important is because not only do they form a vector space, so we'll just make the argument that the generators must be a superposition of all possible antisymmetric matrices. Right? If you lower the indices, they're all antisymmetric matrices. But they're not only a vector space. Remember, they need to obey a Lie algebra. So, what is the Lie algebra? And by the way, this group is called the continuous, if you only include the continuous part of the Lorentz group. So for rotations and boosts, this is called SO3, 1. Right? So this is rotations and boosts. And so remember, why it's important is because the Lie algebra is what determines the group multiplication groups. Right? Remember that e to the x times e to the y is e to the x plus y plus commutators. So if you know the commutation rules between the basis generators, then you know how to do this construction. At least term by term you can write it down. Right? You may not be able to write down the exact formula, but at least term by term you know how to do the commutations. So this is why it's important to know it's antisymmetric, because then you can construct this guy, and then you can show yourself that by a direct calculation that the commutation of J mu nu, you can write this, commuted with J rho sigma is given by I eta nu rho J mu sigma minus eta mu rho J nu sigma, rho sigma very careful with the indices. And then, once you get this straight, the other one would just be the slope between the sigma and the rho. So it will be plus mu sigma, this will be nu rho, and then minus eta nu sigma j mu rho. Okay, I think this is going to be a homework, so I won't do it. Right? It's a little bit tedious, but you should do it once in your life. Right? Just check that this is the real algebra of SO 3,1. Actually, it works in all dimensions, so I should say that this is actually SO D,1. It works in all. D is the number of space dimensions. And the 1, as you can guess, is the time. We will not do the D case because, obviously it gets more and more complicated as you get the higher and higher dimensions. But what we will do is, for the remaining time, we'll talk about the 4-dimensional case. Okay. And in particular, you'll see how to relate it back to rotations and boosts. So let me give you the punchline first. The punchline is that the Lorentz transformation